Yeah, we come back to physics today, but before doing this, I think I should collect the important formulas from pseudo-Riemannian geometry. We have done so much mathematics over the last lectures that maybe it's a little bit hidden what are really the most important points. So I think it's a good idea to highlight the most relevant formulas, which actually will be needed most frequently when doing calculations in general relativity. So let me collect the most important for pseudo-Riemannian manifolds. Yeah, a pseudo-Riemannian manifold is a manifold with a pseudo-Riemannian metric. So we have a metric G, which in coordinate notation is something like this. And virtually anything which is of interest can be calculated from the G mu nu's. And I will now collect the relevant formulas which tell us how to do this. So if somebody gives us a pseudo-Riemannian manifold, this means he gives us a metric, for instance in a particular coordinate system, then we can calculate anything we are interested in on this manifold from these metric coefficients. And I will write now the most important formulas down. So the first thing we get is the inverse metric. So the formula which defines this is this here. That I get the Kronecker if I multiply the metric with the inverse metric with a summation over two indices. And of course I can also do it the other way around, because these are square matrices, right? I have as many rows as I have columns, so every right inverse is also a left inverse. So I have rho, tau, no, not tau, that shouldn't use tau, anything else, G mu tau. So that's the inverse metric. Then we can calculate the Christoffel symbols. We derived this formula last time. What I mean is, of course, the Christoffel symbols of the Levi-Civita connection, which is determined by the metric. And what we got last time, yesterday actually, was this here. This was 1/2. The inverse metric here, and then come 3 terms with partial derivatives of the metric, 2 with a plus, 1 with a minus. And you can easily reconstruct where the minus sign must be from the fact that the Christoffel symbols of the Levi-Civita connection are symmetric. They are torsion-free. So we must arrange the things in such a way that this becomes symmetric with respect to mu and nu. So I have a sigma here, a sigma here, a sigma here, mu, nu, mu, nu, mu, nu. That's the only way in which I get something symmetric. Right? If I interchange mu and nu, then these 2 terms are swapped, but the sum of them remains the same, right? And this is symmetric, so it remains unchanged if I swap the indices. So that's the Christoffel symbols, what we have last time. So they come about by differentiating the G mu nu once. Yeah, they are expressed in terms of first derivatives of the G mu nu. So if I have the G mu nu's, then I can calculate this just by differentiating. And then we have the curvature tensor. Some people call it Riemann tensor, but I always called it curvature tensor, so let's stick with that. And so if we have a connection expressed in terms of Christoffel symbols, then there was this formula how we get the components of the Riemann, of the curvature tensor. There were 4 terms, and half an hour ago I realized that in the script, in the part where I had this formula for the curvature tensor, there are 2 indices wrong. So I'm now very careful now to write it carefully, to write it correctly. And in the next email message I send around, I will correct this error. So I had tau, mu, nu, sigma. So what you should keep in mind is that this is given by 4 terms. It involves, the first 2 involves partial derivatives of the gammas, and the other 2 involve products of gammas. And then the upper index tau is on one of the gammas, always. And I begin by writing these things in the same order as I have them on the left-hand side. And then the next term comes about by interchanging mu and nu and putting a minus sign here. So what you have to keep in mind is that this is antisymmetric in these two indices. So I must get something which is antisymmetric with respect to mu and nu. So I think I keep the sigma, have the mu and the nu here. And here I have a sum, and this was the wrong index. Yeah, in the script there's a sigma. This should not be a sigma. Yeah, sigma cannot be a summation index. So this should be a row, for instance, or something else. And then I have mu, nu, sigma, and again the antisymmetrization. Mu, mu, sigma. So that's the formula for the curvature tensor. So you see, if you give me the metric, I calculate the gammas by differentiating once. And then I get the curvature tensor by differentiating another time. So I can calculate the components of the curvature tensor from the g's. And this is an expression which is second order in the g's. Yeah? It involves second derivatives. And this tells us that in general, that's something I mentioned last time, but I didn't really give you an argument. I forgot to do this when we had this on the board. I mentioned that we cannot have the g mu nu constant on a whole neighborhood unless we are on the flat case. And you can read this from these formulas. Let's assume the g mu nu's are constant, not just at one point, that's always possible, but in a whole neighborhood. Let's assume they are constant in a neighborhood. Then these derivatives give 0, right? So then the gammas are 0 on the whole neighborhood. And then these derivatives and these products give 0. So the curvature tensor is 0. But this is a tensor. So if it's 0 in one chart, then it's 0 in any chart. So let's turn this argument around. If the curvature is not 0, if the manifold is not flat, it's impossible to have a chart where the g mu nu are constant. Yeah? That was this important observation, which I forgot to emphasize last time when we had this formula on the board. So from the curvature tensor, we can then form the Ricci tensor by contraction. That's something which is also very important because it enters into Einstein's field equation. It's just a contraction of the curvature tensor over the first two indices. So it is a tensor of second rank. Yeah? The mu is summed away, and only the indices nu and sigma are left. And with the help of the metric, we can also form the so-called Ricci scalar, or what is the same, the scalar curvature. Which is the contraction of this here. For this I need the metric, nu sigma, g, nu sigma. Yeah, a Ricci tensor is defined for any connection, because the curvature tensor has one upper and one lower index. But if I have done this contraction, then both indices are down. So as long as I don't have a metric, I cannot contract another time. So this only works if I have a metric. Then I can contract another time. By the way, what in English is called contraction, contracting over indices, in German is called Verjüngung. So in German we say that's der verjüngte Ricci tensor. Okay, so these are the curvature quantities, and these will occur in the future frequently. So these are expressions which one really should become familiar with, because they occur in Einstein's field equation. And the geodesic equation is also important. We had this last time in local coordinates. We got this expression. This was last time, yesterday on the board. Nu sigma x nu sigma x sigma dot is 0. So that's the second order equation for the curve in the manifold. And the solutions are the geodesics. This means those curves for which the tangent vector is parallel transported. And it's useful to know that this can be derived from a Lagrangian. So when you actually start calculating with the geodesic equation, then it's always a good idea to use the Lagrangian approach, because the calculations become then much simpler for geodesic equation. And the Lagrangian had the form 1/2, which is a pure convention, but usually it's put there. L is a function of x and x dot. With the x mu nu's depend on x, and then I have x mu dot, x nu dot. So these are the most relevant formula. formulas. Of course, some of the other formulas will also be important from time to time, but these are the most essential ones, which will really make up the basic structure of general relativity. So it would be good if we would become familiar with this. Okay, and now finally we can end this mathematical section, and we can come to section 5, which is about the foundations of general relativity. So in the first part of this section, I will just discuss the geometric framework of general relativity, which is now established by after we have learned all this mathematics. So this is, how did I call it? General relativistic spacetimes. Then we will talk about fields on a general relativistic spacetimes. This will lead us to the famous rule of minimal coupling, which is a sort of implementation of the equivalence principle. And then we will talk about the field equation of gravity. So this is a program for the next, I think, 1.5 lecture or so. So general relativistic spacetimes. What is a general relativistic spacetime? Well, the whole work we did over the last weeks, this mathematical, this learning of mathematical terminology, was motivated by the preceding section where we talked about the equivalence principle. And the idea which came out of the equivalence principle was that a general relativistic spacetime should be something which in small spacetime regions looks like the spacetime of special relativity. And we translated this into mathematics by saying that the tangent space should look like the spacetime of special relativity. Yeah, the idea is that if I have a very small neighborhood, then the tangent space to a curved object is almost the same as the curved object itself. Yeah, this was a geometric idea. And then we have learned all this mathematical stuff, and now we see that a pseudo-Riemannian manifold with the right dimension and the right signature is precisely the mathematical structure which provides us with such a thing. So we formulate as a postulate, and this is of course motivated by the equivalence principle, the following. Equivalence principle. A general relativistic spacetime is a 4-dimensional manifold. Of course, we need 4 coordinates in order to characterize an event. Yeah, usually we use 3 spatial and 1 temporal coordinates. So altogether we need 4. So we want to have a 4-dimensional manifold. And because we want to have on the tangent space a structure of special relativity, we need a metric with a pseudo-Riemannian metric. So the manifold is called M, manifold M, with a pseudo-Riemannian metric G of signature. Of course, we want to have the signature which we are used to from special relativity. We have 1 minus sign and 3 plus sign. So general relativistic spacetime is a manifold M with such a metric G. So we often write it as a couple M comma G. So that's the postulate. And the picture is of course the one we already had on the board when we discussed the equivalence principle. So one should visualize this M as something curved. And at each point we have the tangent space. We have learned how to construct this mathematically in terms of derivative operators. And on the tangent space, let me write the P in another place, so that's TPM. So on the tangent space, we have the structure of special relativity, which results from the metric as this point. So in particular, we have the light cone here on the tangent space. But the whole manifold is curved, so I cannot identify tangent spaces in different points in an obvious way. So this is what curvature brings about. It tells us that the tangent space at one point and the tangent space at another point, they cannot be identified in a natural way. So that's the picture. So the physical idea is, if I consider a very small region of my space-time M, then it doesn't matter if I am on M itself or on the tangent space, and then I could use the formalism of special relativity on the tangent space. And well, if you think of Einstein's elevator, then you might imagine the coordinates here in the tangent space attached to this falling elevator, right? And inside the elevator, you have the same surrounding as in special relativity. Okay, so that's the postulate, and of course. This has a nice feature that the terminology is really fitting. That we say general relativity in comparison to special relativity. This is of course only justified as general relativity is really a generalization of special relativity. So special relativity should be a special case of general relativity. So the special relativistic space-time should be a special case of this, and of course it is. The space-time of special relativity is characterized by the fact that this G admits constant components in a certain chart on the whole space-time, namely these eters. So special relativity, or the space-time of special relativity, that's what we discussed at some length in the first 4 or 5 weeks. In the space-time of special relativity is indeed, as the name suggests, a special case of a general relativistic space-time. Namely, one where the metric G admits a global chart so the global chart is something of this sort. X goes from M to R4, associates with each point P, a 4 tuple, x0 of P, x1 of P, x2 of P, x3 of P, such that G mu nu in this chart, so these indices refer to these coordinates, that they are not depending on x, but rather they take these constant values, which we denoted eta mu nu. This was just a diagonal matrix with these entries, -1, +1, +1, +1. So this is obviously a special case of this. And well, it's a very special case, because then the gammas vanish and the curvature tensor vanishes. So it's a flat general relativistic space-time. And whenever we have something which is not flat, whenever we have curvature, then we cannot introduce such coordinates on an open neighborhood or even on the whole space-time. And then we say we have gravity. Gravity is now coded into the geometry. So gravity is what makes the space-time differ from the special relativistic space-time. If you have special relativity, then gravity is switched off, it's disregarded. And if we switch on gravity, then curvature comes into the game, and then we have a more general space-time than this here. So that's a relation between special and general relativity. Yeah, okay. I should now talk a little bit about the conventions I have used here already, as we were used in special relativity indices x0, x1, x2, x3. So from now on, I will come back to this old convention. So from now on we use again the following conventions. So coordinates on the space-time, and this will in general be a general relativistic space-time, not the one of special relativity, are denoted x0, x1, x2, x3. And the reason why we distinguish one of them by giving it the index 0 is that usually we choose for the x0 coordinate a time-like coordinate. So we choose it in a way that the x0 lines are time-like. Actually, it's not always done this way. There are some applications where it's helpful to do something else, but usually, in most cases, usually we choose the x0 lines time-like. So what does this mean? It means that if I insert the vector field d by dx naught into the metric, so that's the metric coefficient which we would also denote just g naught naught, right? That's a term where mu and nu are both 0. That this here is smaller than 0. What does this mean? It means that if I have my x naught lines here, that then they lie inside the light cone everywhere. Yeah? At each point I have, we look inside the cone. At each point I have this light cone on the tangent space, and then I can check if the tangent vector to my curve is inside the cone or on the cone or outside. And this condition is a condition which tells me that it is inside. This means that these objects which move on these word lines move at subluminal speed. So that's what we usually do. We usually choose the x0 coordinate as a time-like coordinate. So we use the summation convention, Einstein's summation convention. For Greek indices, mu, nu, sigma, or what else, going from 0 to 3. And for Latin indices, occasionally, they will not occur too often, but occasionally I will use Greek indices. They will take the values 1 to 3 only. So when we have a coordinate system where x0 has this property, so where the x0 lines are time-like, then this would correspond to spatial coordinates, right? To the other three which label these x0 lines. So they could be considered as coordinates on space. And another convention that I would like to introduce is del always denotes the Levi-Civita connection. So from now on we will consider no other connections and the Levi-Civita connection of our metric. I think there's no hyphen here in English. And when I use gamma, then I mean the Christoffel symbols of the Levi-Civita connection. So this So in particular, the torsion tensor will from now on no longer occur because it is a torsion-free connection, right? It's symmetric in the two lower indices. We have it still on the board. You can check here. Yeah, this is symmetric. I already emphasized this, symmetric in mu and nu. So these will be our conventions. Okay, so the postulate, as I said, is of course motivated by the equivalence principle. And of course, maybe we should specify this a little bit more. So the equivalence principle, the idea behind the equivalence principle was that on a small neighborhood, I can identify a general relativistic spacetime with a spacetime of special relativity. You might ask, to what order precisely does this work? So how close can I go to the point so that this works? And the answer is we can do it up to second order. Yeah. Well, if I do have a linear approximation, then it always is identical with a manifold to first order. Yeah? Linear approximation means approximation up to first order. But the relevant thing is that also the second approximation works. And for that, we need a mathematical result, which says that we can choose a coordinate such that the metric takes the desired value at a particular point, and also that the gammas vanish. So I will write this down as a theorem, because it is when we really implement the equivalence principle, then this will be of some relevance. So let me write this as a theorem. And the most part of it will actually be proven on a worksheet. By the way, I should mention, for those of you who have not yet noted this, that this week we talked about worksheet 7 again. So worksheet 8 will be the subject of next week. So we have a delay of 1 week, so to speak. The reason is that our friends in Bielefeld are a little bit behind, because there was a problem with uploading the lectures last week. So they appeared fairly late, so late that they couldn't do the worksheet which was due last week. So they postponed it by 1 week, and then we decided to do the same here in Bremen so that we are synchronous with Bielefeld. So the worksheet 8, which I distributed a week ago or so, will be discussed only next week in the tutorials, both here and in Bielefeld. And this worksheet will contain one problem, which actually is the main part of the proof of the theorem I will now write down. Okay. So, well, one can argue that maybe it's not a theorem, it's more like a, I don't know, a proposition or something like that, but let me call it a theorem. It's not really very deep. So let Mg be a spacetime, a general relativistic spacetime, and fix a point P and M. You may choose any point, but it only works at one point. So the statement is then there's a chart. It's defined on a neighborhood of P. Such that the metric in this chart, the components of the metric in this chart at the point P take these values eta mu nu. We have already talked about this. We can always bring the metric at one point to standard form. So for our signature, this would be the diagonal form -1 + 1 + 1 + 1. But the not so trivial statement is that at the same time, we can also have the gammas equal to 0. And the proof, well, the hard part, or the hardest part, it's actually not really hard, it's a few lines, is to prove this here, that there is a coordinate system where the gammas are 0. If we have done this, then the rest is more or less trivial. And this non-trivial part we will do in the next worksheet. gamma mu nu sigma will be proven in, what was it, problem 2, I think. Of worksheet 8. So what we will prove is that whenever we have a torsion-free connection, and our connection here is torsion-free, then we can find a coordinate system such at any one point the gammas vanish. We will do this by introducing first a more or less arbitrary coordinate system and then do a particular coordinate transformation which sends the gammas to 0. So that's what we do in this. I think it's problem 2. Let me check. Problem 2, worksheet 8, yes. And then the rest is trivial. If you have achieved this, then we only need a linear transformation in order to achieve this here. This will not spoil this, because under linear transformations, the gammas behave tensorially. Yeah? So they transform homogeneously. Not under arbitrary coordinate transformation, but under linear coordinate transformations. So then G mu nu can be achieved by a linear coordinate transformation. Coordinate. So I just rearrange my axis, so by a rotation and by stretching the axis in such a way that at this point I get here the standard form. And this will not spoil this here. So that's an important statement if we want to apply the equivalence principle. So we will use this a couple of times in the future when we discuss what the equivalence principle really tells us about the behavior in a small neighborhood of a point. Then we will use this result, that at the point itself we can make the g's to eta and the gammas to 0. This means if we are in a small neighborhood, then the g's are very close to the etas, and the gammas are very small. They are very close to 0. Yeah, so that's a fact which we will use. Okay, and now we can talk a little bit about physics on a general relativistic space-time.
By the g, you don't mean 0, you mean eta.
Oh yes, of course, sorry. No, that's of course not possible because it's non-degenerate, right? So of course it can never be 0. Sorry, this was just a writing mistake. Eta mu nu, of course, yes. Thank you. Okay, so in order to fill this postulate, is it still on the board? No, I think I've just erased it. This postulate that a pseudo-Riemannian manifold is a general relativistic spacetime. Of course, we need to know how to associate geometric objects on such a manifold with physics. Yeah, if we associate this with physics, and I will now list a few relations between geometric objects and physical interpretation, which are important if we are just talking about the geometric background of general relativity. So for this, we will only be concerned with the motion of particles and light rays. And in the next section, I will then talk about fields. Of course, we can also use fields in order to probe general relativistic space-time. So let me just write interpretation. So what objects in a general relativistic space-time can be associated with physics? So the first thing, obviously, just for the sake of completeness, I write down what probably everyone was assuming without that it goes without saying. The points in M, of course, are events. Yeah? So every point is an event, something which happens at a particular time at a point in space. So we are used to this four-dimensional view from special relativity, that we do not speak about points in space and time, moments of time, but that we combine them into four-dimensional entities. So these are the points in M. Then in special relativity, we had particles moving on time-like curves, right? So requirements that something is a particle, a massive particle, was that it should be inside the light cone. It should not move at a superluminal speed and not even at the speed of light. So it should really be inside the light cone. So that's what we interpret as possible world lines for particles. And precisely the same thing we formulate now for general relativity. We have the light cone at each point, so we can classify curves, world lines in the space-time according to being time-like, space-like, or light-like. And again, as in special relativity, we say that the space-like curves are possible world lines of massive particles. So a space-like, sorry, did I say space-like? Time-like, of course. A time-like curve in M is the world line, or a possible world line. Of course, not every time-like curve is really realized. Yeah, let me write it this way. It's a possible world line of a massive particle. So this would be in coordinate language something of this sort. Yeah, it would something which is an x of tau, where x has 4 coordinates. So it's something like x0 of tau, x1 of tau, x2 of tau, x3 of tau. And the property that it be time-like is that the tangent vector to this curve is inside the light cone. So it should satisfy the condition that g mu nu at x of tau, x mu dot of tau, x nu dot of tau is smaller than 0. And if this is true, then we can do the same thing which we did in special relativity, namely we can fix the parametrization by normalizing this object. This should have the physical dimension of a velocity. So the natural way to normalize it is, because it's negative, to minus c squared. That's what we did in special relativity, and we do the same thing here. So it works perfectly well also in general relativity. So we fix the parameter by requiring that this expression is minus c squared. So in many books you will find that c is set equal to 1, and then it just fixed by setting it to minus 1. But I try to have the c's always in the right place. And to remember how we called this parameter tau in special relativity, if it satisfies this property, had a special name. Proper time, yes. And of course we use the same name here, right? And the clock which shows proper time is called a standard clock. So tau is called proper time. Okay, so in special relativity, there were special time-like curves, namely the inertial curves. Yeah, particles which move just in straight lines uniformly. These were the inertial motions, which established actually the mathematical structure of the special relativistic space-time. Now on a general relativistic space-time, we don't have anything of this sort. We don't have inertial motions. And that's fairly clear that we cannot have something like that, because if we switch on gravity, and that means going from special to general relativity, then of course we won't have any longer particles moving in an inertial way just in straight lines. They will be affected by gravity. So the best thing we could do is we could consider particles which are affected only by gravity, by nothing else. And that's what we call freely falling particles. And they should be the ones which come as close to the inertial motions as possible. So in very small regions, they should move like the straight lines in special relativity. And this is realized by the geodesics. The geodesics are the curves which are as straight as possible. With the help of this theorem, I will show in a minute that they are actually straight up to including second order. Yeah? So that's what I mean by they are as straight as possible. They cannot be straight to arbitrary order, but they can be straight as to up to second order. And that's actually what they do. So the freely falling particles, the geodesics, they are the natural generalizations of the inertial motions in special relativity. So we will consider them in the next item. So among all possible time-lag curves, among all possible motions of massive particles, the freely falling particles are distinguished by the property that they are geodesics. So a time-lag geodesic is a possible, again, world line of a freely falling massive particle. And freely falling means influenced by gravity alone. If you are on a general relativistic spacetime, then gravity is automatically coded into the geometry. It is there. Yeah, we cannot switch it off without going back to special relativity. So if we are on a general relativistic spacetime with a non-zero curvature, then gravity is switched on. It's coded into the geometry. It's not a field on the spacetime. It's part of the geometry of the spacetime itself. And so the only thing we can consider is particles which are affected by nothing else. They are only affected by the geometry. And that's what's meant by freely falling, of a freely falling massive particle. So then we have, again, something of this sort. Yeah, it's, of course, a special case of this here. So we have, again, something with 4 coordinates which depend on tau. Again, we use proper time. That's our convention. So our convention is that g mu nu x of tau, x mu dot of tau, x mu dot of tau is minus c squared. And then in addition, the geodesic equation should hold. I had it on the board 20 minutes ago or so. The geodesic equation is x mu double dot plus gamma mu nu sigma. Maybe I should write the x's everywhere and the tau's maybe also, just for the sake of clarity. Yes, I think that's a good idea. So this, of course, depends on tau, right? So the dot means differentiation with respect to this parameter tau. Then I have the gamma, which depend on x of tau. Yeah? They are functions on the spacetime. So I follow the path of the curve, and at each point x of tau I evaluate the gammas. And then I have x nu dot of tau, x sigma dot of tau is 0. So these are the equations which fix time-like geodesics, freely falling particles. So that's the analog of particles that satisfies the Newtonian equation of motion in the gravitational field. Yeah? So that's the analog in general relativity. So here's a 0. So in a sense, there's no force acting on these particles. And this reflects the fact that gravity is coded into the geometry. Yeah? Gravity does not produce a force onto the particle. It is just the motion under gravity alone is the motion which just follows the geometry, nothing else. So this was about time-like curves, massive particles. And I hope you remember that in special relativity we also discussed photons to some extent. And by that I always mean a classical photon, yeah, not these quantum objects which you study in quantum field theory or something like that. I just mean a classical particle that moves at the speed of light and which moves in special relativity on a straight line. So it was the analog of massive particles in inertial motion, now for the case of a massless particle which moves at the speed of light. And obviously the analog in general relativity is that we consider now light-like geodesics. Yeah? The straight lines are replaced by geodesics, and the property that the object moves at the speed of light means that the tangent vector lies on the light cone. So that the tangent vector is light-like. So that's what we could call classical photons in general relativity. And these two objects, the time-like geodesics and the light-like geodesics, are really crucial if we want to investigate particular general relativistic spacetimes, what we will do a little later. Namely, that's a way in which we can observe the effects of a gravitational field on objects which we can really observe. So we can measure the path of a freely falling particle, or the path of a light ray, which we may think of being realized by classical photons, and we can see if the prediction from general relativity coincides with our observation. So these are the tools, the most important tools by which spacetimes can be probed. Okay, so that's the next point. A light-like. And here we only consider geodesics. Of course, we could also consider light-like curves which are no geodesics. This would be objects moving off the speed of light, but being influenced by something in addition to gravity. Yeah? There's not much physical relevance to this. Of course, if you have mirrors or something like that, mirrors which just deflect photons, then of course the whole thing would not be a geodesic, it would be a broken geodesic, right? But well, that's not so particularly interesting. So here we have no analog. We don't discuss an analog of this here. We just discuss only an analog of this here. So a light-like geodesic is again a possible word line of a classical photon. So this means it is an object which also has 4 coordinates, just like a massive particle. So it's also given by a curve, but for some reason I call the parameter not tau, I call it s. I will say a word about this s in a minute. So for the moment it's just a curve parameter. x3 of s. And in this case, it should satisfy the following 2 conditions. So it should be a light-like curve. This means where we had the minus c squared there, we now have 0. Yeah, so it has g mu nu at x of s, x mu dot of s, x mu dot of s is 0. This means it's light-like. This tangent vector is always on the light cone. Yeah, that's what this equation means. And it should be a geodesic. The geodesic equation looks precisely the same as there. So x mu double dot, oops, only 2 dots, not 4, s. Plus gamma mu u sigma x of s, x mu dot of s, x sigma dot of s is 0. Yeah, what about the normalization? What we did here, yeah, we had the time-like curve. Here we had smaller than 0 sign. And then we normalized the tangent vector, which fixed the parameter. And well, here we cannot do this, because here normalization is not possible if we have the 0 here, right? So we have already talked about this in special relativity. So a way of saying is that, that we say there's no proper time for photons. Yeah? Photons do not have a proper time parametrization. So we could ask, to what extent can we fix the parameter s? And well, just from the equations which are on the board, and there's no reasonable way of imposing an additional condition, just from these two equations, the s is fixed up to a so-called affine transformation. This fixes s up to affine transformations. What is an affine transformation? Well, it's a linear transformation plus an inhomogeneity, plus a constant. So this means if somebody has such a parameter S, which so that these two equations are satisfied, then we can make a transformation from S to another one, say S hat, of the form k times S plus S naught, where k and S naught are constant. That's what we call an affine transformation. Yeah? This would be a linear transformation, and if we allow ourselves to add a constant, then we call it an affine transformation. So this means linear and inhomogeneous. This fixes S up to affine transformations with k and S naught constant. And actually, well, this is just a claim, but it's fairly easy to verify this, that if we have a solution of this equation, then a reparametrization of this curve is again a solution, if and only if the change of the parameter is of this form. And this will be done again on a worksheet. I think it's again worksheet 8. Where are we? Yes, problem 4 of worksheet 8. Problem 4 of worksheet 8. So for light-like geodesics, we are in the situation that there is a certain freedom in choosing this parameter. Namely, it's only fixed up to such an affine transformation. And for this reason, the parameters which satisfy this equation are called affine parameters. Yeah? So we say a geodesic admits a whole family of affine transformations, and they are related by this transformation. So there's not one particular distinguished parameterization for a classical photon, for the world line of a classical photon, in contrast to the time-like geodesics, where we have the proper time parameterization. Okay, well, the proper time parameterization, of course, also has this freedom here, yeah, that we can choose a zero wherever we like. Yeah, we could add a constant to the parameter. So this means just we choose the zero on the dial wherever we like. But there's no freedom which corresponds to this here for the proper time. So in a sense, the unit, yeah, the rhythm with which the clock ticks, this is fixed. And here we have, we can stretch or compress the tangent vector with an arbitrary constant factor, which reflects the fact that there's no distinguished time along a world line of a photon. Okay, so much for time-like and light-like geodesics. And as I said already, these two objects are particularly interesting because they can be used to probe a space-time. We have a space-time, a particular model for a gravitational field, and we want to study physics in this space-time, then we throw particles into this field, and we use this equation in order to calculate how they move. And if this is supposed to be a model for a particular part of the universe, then we can check if the particles in nature really move in the way as our model predicts, and the same for light rays or classical photons. Okay, having talked about light-like and time-like geodesics, I can now specify this remark which I made earlier in connection with the theorem. So with the help of this theorem, we can now ask to what extent do these three equations for time-like and light-like curves, the geodesic equation, to what extent are they can they be approximated by the special relativistic situation? So if we follow freely falling particles or photons in a general relativistic spacetime, to what extent can this be approximated, to what accuracy can this approximated on small neighborhoods by the special relativistic equations? And what I said already and what I will demonstrate now is that it can be done up to second order. Yeah, so if you go up to second order away from our point P, then we can work with the equations of special relativity. And, well, these coordinate systems, these are the coordinate systems which you may think of as being realized by Einstein's elevator. So how do I want to write this? Let me check this. Yeah, so the claim is in a coordinate system with these properties from which we have established that they exist in a coordinate system with G mu nu at P is eta mu nu, and gamma mu nu sigma at P is 0. My claim is geodesics are straight up to second order. Yeah? To say that something is straight up to first order is trivial, because everything is straight up to first order. First order means approximated by a linear map. This means by a straight line. But the non-trivial statement is that it works even one order higher. And we can do the following. So if we have a geodesic, say we have a curve x mu of tau, which is a geodesic, then we can approximate it. So let x mu of tau be a geodesic with x mu of 0, say, as our point P. Yeah, we arrange things in such a way that it passes at tau equals 0 to the point P. So then we can write a Taylor expansion. We can write x mu of tau is what? It's x mu of 0. That's a 0th order approximation. Then plus tau x mu dot of 0 plus, what is it, tau square over 2, I think, x mu double dot of 0, and then the terms of third and higher order. Okay, that's just standard Taylor series expansion. And now we have a geodesic. So this is minus gamma mu sigma. When tau takes the value 0, we are at the point P. Yeah? So this is at the point P. And then x mu dot of 0, x sigma dot of 0. Yeah? So here I have introduced the geodesic equation. The fact that x mu dot plus this expression is 0. That's the geodesic equation. But the gammas are 0 at P. Yeah, we are in a coordinate system where the gammas are 0 at P. So the whole thing is 0. And that was a claim that up to second order it is a straight line. So let me write the result here. I.e. x mu of tau is x mu of 0 plus tau x mu dot of 0. That's a straight line, right? That's the equation of a straight line. And now the second order term is not there, yeah, because it comes with the coefficient 0. So the next term is already the cubic term. So up to second order, it is a straight line. That was my claim. So if you want to depict this, I could do it in such a way that you here have, well, that's a very small neighborhood. I draw it not so small so that you can see something, but think of this as being small. So this is attached to a point P, and this is very small. So in this region, in this small region, the geodesics can be considered as being straight lines. And then here away, then the curvature becomes, then you can feel the curvature. So this is here a neighborhood of second order. Yeah? Up to this order, we have straight lines. So that is the statement which is meant by saying that in sufficiently small space-time regions, we have the same situation as in special relativity. Yeah, sufficiently small means that all terms higher than second order can be neglected. Yeah? So then in particular, the geodesics are straight lines, so they are like the inertial motions in special relativity. So if I am in a box or something like that, to which these coordinates are attached, and the box is so small that I'm inside this neighborhood, then inside this box, I don't see a gravitational field. Yeah? So I see just my objects which are freely falling. I see them moving on straight lines, like in special relativity. So that's the idea behind Einstein's elevator, right, which we discussed at some length in section 3. So that's a mathematical realization of this idea. It is this, in this fact that the gammas can be made to 0 at one point. That's a mathematical fact which allows us to draw this conclusion. Okay, anything else about particles? No, I don't think so. So then we can talk about fields a little bit. So this was establishing the basic geometric facts of general relativity and connecting them with physical interpretation. So we were just talking about time-like and light-like curves. That means about particles and photons. And now we will talk about fields. Of course, we also want to consider fields on our space-time. So the question is, of course, we will again use the equivalence principle. That's the guiding principle for the whole theory. So we will ask ourselves, if we know a field equation, for instance, for the electromagnetic field, the Maxwell equation, or some other field equation, if we know it on special relativity, how do we transfer this into general relativity? That will be the question I want to discuss now. So another way of asking the same question is by saying, how do these fields couple to gravity, right? Going from special to general relativity means to switch on gravity. And switching on gravity means asking how the objects which I had on my space-time couple to gravity. And where there's a method, a prescription of how one could do this, how one could switch on gravity, how one could switch on this coupling, it's not compelling. So the equivalence principle doesn't say that one has to do it in this way, but it's the simplest method which is compatible with the equivalence principle. And for this reason, it's called the rule of minimal coupling. And actually, quite a lot of physical laws come out correctly. Not all, but quite a lot of them. So the next section will be the rule of minimal coupling. And we know how to handle fields on our space-time. And then in the next section, we will deal with Einstein's field equation. So that's 5.2. The rule of minimal coupling. So consider field equations in special relativity. So let's assume we know how a field theory for a particular type of field works in special relativity. So actually we have discussed two types here in the lecture. So we have discussed the electromagnetic field. So the field equations in this case are the Maxwell equations, right? And we discussed how they could be written in a special relativistic context. So we have written them in special relativity in inertial coordinates. We also talked a little bit about continuum mechanics. So there also occurred fields for velocities, densities, pressures, and things like that. So another possibility could be the let me write fields from continuum mechanics. So examples would be the for velocity, the mass density, and the pressure of a perfect fluid. This was one of the models we studied a little bit in one of the worksheets of a perfect fluid. This includes the dust case as a special case, right? If the pressure is 0, then a perfect fluid becomes a dust. We talked a little bit about the energy momentum tensor and the equation of motion for perfect fluids. So we could consider such a field on special relativity. There are other fields. I'm sure all of you have heard about the Dirac equation. Yeah, so we could consider. I will not deal with the Dirac equation here in this course, but I want to mention it, that this also would be a field which fits into this framework. So we could consider Dirac fields. And then there are also, for instance, Klein-Gordon fields. And others. So we know how to handle these fields in special relativity. Yeah, we know the equations. We have established the whole theory. And the question is, in which way do these equations carry over to general relativity? Is there a rule how we can write the general relativistic equations if we know the special relativistic equations? And the guiding principle, of course, is the equivalence principle. But the equivalence principle doesn't fix the general relativistic equations uniquely. Because obviously there are many different general relativistic equations which go over into special relativity if we consider small regions and make this approximation up to second order and so on. So it's not unique. But there is a prescription which gives us in a very simple way a general relativistic law which is compatible with special relativity. And as it is the simplest way of doing it, it's called minimal coupling. So I will write this now down. So how can we transfer or translate? Yeah, I think translate is better. Yeah, or generalize. How can we generalize? That's even better. Can we generalize these, what did I write, field equations? Such that the equivalence principle is satisfied. The easiest method, or the simplest method, not the only possible way of doing it, but the simplest method is by the following prescription. And that's the rule of minimal coupling. Yeah? So it's a prescription or a recipe. It tells you precisely what to do, and if you are lucky, you really get the correct law for general relativity. So this is called the rule of minimal coupling. So it tells us, it gives us a certain rule how to switch on gravity, how to couple the field to gravity. And it says the following. Begin by writing the equations in special relativity in inertial coordinates, what we always used. Yeah, these coordinates which are related by Lorentz transformation. We always use these coordinates in special relativity. And when we wrote down the electromagnetic equations and the continuum mechanics equations, we did it in these coordinates. That's the starting point. So the starting point is write the field equations in special relativity in inertial coordinates. Then you will have etas flying around. Yeah? The metric in inertial coordinates is expressed in terms of these etas, which we always had in special relativity. And you will have partial derivatives flying around. And these two things have to be replaced by something else. And then we are in general relativity. So the rule is then replace eta mu nu which will occur in these equations, right? Remember Maxwell's equations. We had raised and lowered indices with the eta. So the etas enter into Maxwell's equations in special relativity. And also in the energy momentum tensor of the electromagnetic field in general relativity. The eta also enters into the Euler equation for a perfect fluid. So there are etas flying around. And we replace them by g mu nu, the general relativistic metric. And we have partial derivatives. Of course, Maxwell's equation involved partial derivatives. The Euler equation involves partial derivatives. So you replace the partial derivatives. That's not an equality. By g mu nu, I meant. By g mu nu, and replace the partial derivatives by covariant derivatives. And our convention was this means the Levi-Civita connection of the metric. And the claim is this gives the general relativistic equations the correct physical laws for the corresponding fields in general relativity, and now in arbitrary coordinates, in arbitrary coordinates. So you can do this with every equation, every field theory which you have in special relativity. And we will do it in a minute for the electromagnetic field and for a perfect fluid. We will see what sort of equations we get. Obviously, this is compatible with the equivalence principle. Namely, if we have the equations now in general relativity in arbitrary coordinates with these replacements, then we can make a coordinate transformations around any point we like, such that in the new coordinates, no, not these ones, these conditions are satisfied. Yeah, that the g's becomes the etas and the gammas become 0. And then obviously the g's go over into the etas at the point, and the covariant derivative goes into the partial derivative because the gammas is 0. Yeah? So you reproduce then the old laws in sufficiently small neighborhoods. So this is compatible with the equivalence principle. But of course, it's not the only way of doing it so that you are in agreement with the equivalence principle. You could do something more complicated. So that's the reason why it's called minimal coupling. It's the simplest method which you could apply. So if you have produced the new field equations in this way, then you have to check if this is really realized in nature. Yeah, so it's not a law of nature that this rule works. It's more like a rule of thumb, yeah, which in some cases, actually in many cases, gives the correct laws. But you must be aware of the possibility that sometimes it might give you something which is not correct. Well, what could go awry? What are the problems? Well, there are two problems actually. The first is that the rule is not unique. Namely, whenever you have second partial derivatives, then you don't know how to order them. Yeah, at the special relativistic level, where the partial derivatives occur, the order doesn't matter, yeah, because you can commute the partial derivatives. But now you replace them by covariant derivatives, and the covariant derivatives do not commute. Yeah? So if you have written the partial derivatives in this order first, then you get a law of nature in general relativity. If you have written it in the other order, which in special relativity is precisely the same law, you get a different law in general relativity. Yeah? So you have to check which one is the correct one. So the first observation is the rule does not give a unique result when second derivatives occur. So fortunately, Maxwell's equation and the Euler equation involves only first derivatives. Then this problem doesn't occur. But you may think of some sort of field equation which involves second derivatives. Then you come across this problem. The rule does not give a unique result when second derivatives occur. And the reason is, At the special relativistic level, the order doesn't matter because the two things commute. But at the general relativistic level, when you have replaced them by covariant derivative, then you observe that you get two different things, depending on the order in which you have written the derivatives in the first place. And the second observation is, in addition, one could always add curvature couplings. Yeah, terms which involve the curvature tensor. As the curvature tensor goes to 0, if you go to special relativity, these terms simply drop out. So, as I said, one would have to check which is a correct law of nature. So if it really is this, which you get from the rule of minimal coupling, or if you have to add additional curvature terms, one could always add curvature terms which go to 0 in the special relativistic limit. And for this reason, they are compatible with the equivalence principle. So these are two caveats when we talk about the rule of minimal coupling. But it's nonetheless it is a very useful tool just for guessing the right general relativistic laws. And as I said, for many problems, it really gives the correct general relativistic law as it is checked by nature. And we will now do two examples of this sort: the Maxwell field and the perfect fluid. How much do I have? Yeah, I think I can do the Maxwell field today. Let's leave this on the board. So the things we learned in special relativity, they are useful in general relativity, right? We don't have, it's not a good idea to forget everything about special relativity when we start to do general relativity. A lot of things can be carried over. You just have to keep in mind that the etas have to be replaced by arbitrary components of a metric tensor G mu nu, and that the partial derivatives have to be replaced by covariant derivatives. Then in many, many cases you get the correct general relativistic laws. And that's in particularly true for the Maxwell field. So I will now write Maxwell's equation as we had them in special relativity, and then we will see what the rule gives us for general relativity. And actually it will give us the correct general relativistic version of Maxwell's equation. Okay, so two examples. I think I will only do one today. Oops. So the first example is the electromagnetic field. So in special relativity, we had the following equations. Hope everybody remembers. Discussed Maxwell's equations in 4-vector notation to some extent. Not too much detail, but a little bit. So we had the two Maxwell equations. The first one was d mu f mu sigma, and then the cyclic permutation. D nu f sigma mu plus d sigma f mu 0. And the second equation was for the other second rank tensor G. This was J nu. So these are Maxwell's equations. Yeah, these are Maxwell's equations. Important consequence of the second Maxwell equation was the law of charge conservation. As a consequence, because the G mu nu is antisymmetric, we find that E nu G nu 0. This was charge conservation. And we also talked about the energy momentum tensor. This was in one of the worksheets. Let me write it here. And this is the energy momentum tensor in vacuum. I only discuss this in vacuum. So for the case that the G is essentially the same as the F, just up to this constant mu naught, this permeability of vacuum. Because there are problems with the energy momentum tensor in general, which I wanted to evade. So here I have 1 over mu naught. Yeah, that's this constant, this permeability of vacuum, which in the older literature is set equal to 0, but we are now forced to consider it. How are the indices? F, the first one, then the summation index. So F mu tau, F tau nu, minus 1 over 4. And in special relativity, we had an eta mu nu, and then F rho sigma, F rho sigma. So this was the energy momentum tensor. And now we can see what we get from the rule of minimal coupling for general relativity. So how do Maxwell equation, charge conservation, and the energy momentum tensor look in general relativity? If we trust the rule of minimal coupling, and this yields for general relativity. What? So what I have to do is I have to replace any eta. Here, for instance, is an eta by a G, and I have to replace any partial derivative by a covariant derivative. So Maxwell's equations are now this here. Plus del nu F sigma mu plus del sigma F mu nu is 0. And this becomes a covariant derivative. And well, actually here when we derived this equation and played around with this equation, we always raised and lower indices with eta. Now, of course, if we translate this, then we raise and lower indices with G. But because at the same time we replace the partial derivatives by covariant derivatives, we have no problem with raising or lowering indices. Because the process of raising and lowering indices could be done under a covariant derivative. We talked about this last time. Yeah? Not under partial derivatives, but under covariant derivatives. So actually I don't have to care about the fact that here maybe we have raised this index mu with the eta when we played around with these equations. So this can be done safely under the covariant derivative with a G. So we would get this equation here. So this would be now the general relativistic form of Maxwell's equations. And actually it is the general relativistic form of Maxwell's equation. That's what is in agreement with all observations. The law of charge conservation now is this here. So this is charge conservation. And the energy momentum tensor is, it looks almost the same. The only thing where I have to change something is I have to make this eta into a G, right? F mu tau F tau nu minus 1 over 4 g mu nu. Yeah? Components of the metric tensor in arbitrary coordinates. F rho sigma, F rho sigma. So that's energy momentum tensor. In vacuum. Oops. And maybe I should mention here also that we had for a closed system, this means if the electromagnetic field doesn't interact with anything else, so there are no sources and no other sort of, no sources, no forces acting from outside, there's only this electromagnetic field in the world, then we would call it a closed system, and then we had this conservation law, and we write it in this way. Again, raising and lowering indices with the eta, here in special relativity, naturally translate into raising and lowering indices with a g on the general relativistic side. So here we would have for a closed system, well, we had to replace a partial derivative by a covariant derivative. So we would get del mu t mu nu equals 0. So this would give us a condition on the energy momentum tensor that this electromagnetic field is alone in the world, that there are no sources and no forces acting on it. So in general, if we do have sources and if we do something with the electromagnetic field from outside, then this would not hold. Yeah? But for a closed system, it would hold. Yeah, I think time is out now. So this was the electromagnetic field. We will do a few exercises in this relation where there are a few questions you might ask. Well, here I said that this is actually a consequence of this here. Yeah, we derived it. It's very simple. Yeah? You apply the partial derivative with respect to x nu to this equation. You use that this is antisymmetric. Partial derivatives commute, so this term is symmetric, so the whole gives 0. Yeah, it's one line to derive this here from this here. But now we have replaced the partial derivatives by covariant derivatives. And you may ask, are these two equations still compatible? As it's a typical sort of question you have to care about if you use this rule of minimal coupling. It might give you something which doesn't work. So you really have to check if these two equations are now compatible. And in fact they are. We will do this in the worksheet. Here you will see that again, this is a consequence of this here. And you will also see, that might come as a surprise, that actually in this equation we can again replace the covariant derivatives by partial derivatives. This don't change anything. Even in a general relativistic context, in arbitrary coordinates, it is just the same if you write this combination for an antisymmetric f or if you write this equation. So here it doesn't matter if we work with covariant or with partial derivatives, but in general it makes a big difference. So here, for instance, it does make a big difference. So in the that would be worksheet 9, I think, we will do these two things. We will show that this is a consequence of this, and we will show that here we can, if we like, again, replace the covariant derivatives by partial derivatives. So, well, and if you believe that this gives the correct law of nature, then we know how to handle electromagnetic fields on a general relativistic spacetime. We now have Maxwell's theory on a general relativistic spacetime. Okay, next time I will do the same thing for the perfect fluid. So in particular, we will talk again about the energy momentum tensor of a perfect fluid. And then we are prepared for attacking Einstein's field equation, finally. Okay, have a nice weekend.